There from Lupus Luna called Rabbit on the Moon here on Kiwi. Time now is 9:38.
The Radio Wammo Breakfast.
The Geek Show.
Joining us in the Geek Show today, it's Calvin over there. Good morning to you, Calvin.
Good morning, Wammo.
And today we're looking at nanotechnology, the really small stuff, the latest developments in nanotechnology.
Yes, indeed. The tiniest things that we do at the moment. So most of what I'm going to report on today isn't about any new things that are coming out. They're new things that are happening in labs that will influence what technology and which directions technology go in the next 5 to 10 years.
The real cutting edge.
Yeah, absolute bleeding edge, most of this stuff. So you'll need your imagination hats on to see where this is going.
All right, strapping it on now. Cool.
Okay, excellent. Right, well, at the moment, a lot of bottlenecks in modern electronic devices are focused around the data flows between one piece of really high-performance silicon and another. So, we can make these fast chips and fast memory, but there's bottlenecks between them. Now, we've used optical solutions in large-scale applications, such as high-speed internet connectivity, for years now, fiber networks and stuff like that. But there's a key reason why the interface between optical fiber and the electronic world hasn't appeared on chip yet. And that's fundamentally the temperature range at which the materials involved grow on the silicon wafers. They're incompatible manufacturing methods. But recently, and this is only in the last month or so, a team at Berkeley have developed a process to overcome these obstacles, and they're now growing tiny nano lasers directly onto silicon at 400 degrees C, which is a temperature compatible with current CMOS fabrication methods. So this could be developed utilizing all the current manufacturing capability. So these lasers are integrated, they're put on after the normal electronics layers fabricated, and the structure is that of a gallium arsenide conical tower about 500 nanometers wide at its base, narrowing towards its top at about 3,000 nanometers high, with an indium gallium arsenide core where the lasing occurs. So to try and give you some sense of scale on this, because these numbers mean nothing to most people, the tracks on a modern GPU are about 40 nanometers wide. So if they were roads, this would be a tower 250 meters wide at the base and 1.5 kilometers tall.
Wow, extraordinary.
So, quite large in terms of chip components, but obviously this is incredibly tiny.
Yeah.
So this is a critical component for future improvements in processing speed. Instead of hundreds of copper tracks on a motherboard taking data from one piece of silicon to another, CPUs and storage and the like could communicate by a whisker-thin fiber optics, shifting a lot more data at much higher speeds. So this is one of these critical technologies that's going to allow Moore's law to continue and allow computers to keep doubling in speed every 18 months.
Cool. All right. One thing I know that we've talked about on the Geek Show before with nanotechnology is batteries.
Yeah. Well, battery technology is coming on in leaps and bounds, really, as more and more there's more and more demand for batteries and more demand for these batteries to do things. So a team led by Paul Braun in Illinois have developed a 3D nanostructure for making battery cathodes that allows for much faster charging and discharging. So to quote him, they've got a system that gives capacitor-like power with battery-like energy. Most capacitors store very little energy, but they can release it fast.
Yeah.
Most batteries store a reasonably large amount of energy, but they can't provide it or receive it rapidly. This does both. So the practical upshot of this is phones that charge in seconds and laptops and cars that charge in minutes.
That would be handy. It would probably be a good trade-off if it didn't have a large charge, like it didn't last you all day. But if you could just charge it in a few seconds, then you wouldn't, that wouldn't be such a bad thing.
It wouldn't matter as much, would it?
Yeah.
It's like if you only had 150 kilometers range on your car, but every 150 kilometers you only had to stop for 5 minutes to have a coffee and a charge.
Yeah.
I think that would be acceptable to most people.
Definitely.
So the key to how this works is basically they're making a foam scaffold. They do it by coating a surface with tiny spheres, so the spheres are packed as tightly together as possible. Then they fill the space between around the spheres with metal, and then the spheres are melted or dissolved, leaving a metal scaffold like a sponge. They then use a process called electropolishing to really etch away the surface of this scaffold to enlarge all of the pores where the spheres were to make a really light open sponge framework. And then they coat this sponge with a film of whatever active material you need in the battery. So this has been demonstrated with nickel metal hydride and lithium-ion technologies. But the structure is so general that any battery material can be deposited in there and used. So it's like a universal formula to better batteries.
All right. Any more advancements in the battery field of things?
Well, yeah. I mean, batteries are essentially the batteries we're used to are a form of fuel cell. It converts chemical energy into electrical energy, and in one of the more common forms of fuel cells, usually involving hydrogen. The key factor determining the performance of the fuel cell is the efficiency of the oxygen reduction reaction, which is usually happens because of a catalyst. This is the process that breaks the bonds of oxygen molecules. So currently the best catalyst and the one most used in hydrogen fuel cells is platinum. Right, so as well as being expensive, it's unstable when active inside a fuel cell, so it doesn't actually last forever in there, and it's a very limited resource. Yeah. So that hampers the scaling of fuel cell technology totally. But work from Liming Dia, who's currently the Kent Hale Smith Professor at the Department of Chemical Engineering at Case Western Reserve University, he previously demonstrated catalyst performance using nitrogen-doped graphene, which would allow for a metal-free fuel cell, but the complex preparation methods for this precluded commercial use. But a couple of weeks ago, he's just released a paper demonstrating a carbon nanotube-based solution with greater performance and durability than platinum that could potentially be manufactured in a cost-effective way. So this could be the key to replacing many metal catalysts, not just those in fuel cells.
That's extraordinary, and as you say, quite good. Not only maybe on the pocket, but also on the environment as well.
Yeah, very important ecologically because this is taking a very common element and replacing something that platinum, like gold. It's rare and it takes a lot of energy and chemicals and nastiness to get out the ground.
What about, are there any other advances perhaps in the environmental side of things, using nanotechnology to further green tech?
Well, yeah, I mean, one of the problems, and this is something we suffer from a lot in this country, is we use a lot, well, everybody uses a lot of synthetic ammonia fertilizers. This is basically nitrogen with 3 hydrogen atoms attached. An over-application of this builds up nitrates in the soil. This is the waste product where those 3 hydrogen atoms have been replaced by 3 oxygen atoms. So it goes from NH3 to NO3. So this waste product is a groundwater poison, and it's a food source for harmful algal blooms. So, and this has been happening in this country.
Yeah.
And to top this off, the industrial manufacture of synthetic ammonia is an energy-intensive process, and it contributes significantly to atmospheric greenhouse gases. So anything that could, say, take this waste product of NO3 and turn it back into NH3.
And seems like we might have lost our connection there with Calvin, but he was talking about this idea that you can turn that waste product of nitrogen with 3 oxygen atoms back into ammonia fertilizer, and it requires replacing the oxygen atoms of NO3 with hydrogen, which is a fairly difficult chemical trick. And Calvin, you back there with us?
Am I?
Yep.
Have you got me?
Yep. I was just continuing our conversation there. We were just talking about how it's a difficult chemical trick, but there's been a research team
Yes, I could overhear
there.
you.
Yeah.
Yeah, well, a research team led by Miho Yamauchi and Masaki Takara from the Riken Spring 8 Center in Harima have discovered an almost ideal way to do this. They're using photoactive copper-palladium alloy nanoparticles as catalysts. These use solar energy to generate hydrogen gas from water and at the same time catalytically convert the NO3 back into NH3 using these hydrogen molecules they've just freed. So this is a really efficient route of turning this waste product back into fertilizer free from carbon dioxide emissions. So this has turned what was a wasteful, horrible way of making more food into a fully recyclable resource powered purely by the sun.
Brilliant, and hopefully highly relevant and part of perhaps our greener future here in New Zealand. Thanks so much, Calvin, for that. People can find this video and some of the links to what we've been talking about up at thegeekshow.com, 2 3s rather than 2 E's, and of course Calvin over on Twitter as well, twitter.com/CHELFYN. We'll see you next time.
Okay, see you next time.